problems. So after yesterday, you might have realized a couple of things. That is, even with a simple deep network, you can explain several things in neuroscience if you appropriately constrain the network. Like, for example, in case of the stroke model, you might have seen that if you make a bilateral CNN, which imitates the two hemispheres of the brain, right? And then you can explain a lot of things about how to train it, what's the optimal kinds of rehab under various conditions of stroke lesions and all that stuff. But the thing is, deep networks are good only up to a point because basically brain is a very dynamical uh, organ. That is, there's constant change of state variables in the brain. So how do you capture that? The deep networks that we have seen, they're all static networks. They're simply feed-forward networks. So they can't capture the dynamics because even if you present the brain, train the brain on a simple static classification task like MNIST classification, you present an image of a number and then you ask the person to classify it. Even during that process, brain is dynamic. Even in sleep state, brain is completely dynamic. So you can reduce or you can express the dynamics in terms of various frequency bands, from alpha, beta, gamma, delta, and all that stuff. So whereas in case of a deep network, there are no such frequencies, there's no oscillations. So how do you create a deep network where there are oscillations? So that is a big question now. We'll be pursuing that from now on. And and then I'll start with very basic fundamentals and then work towards creation of a deep network with oscillations. Just a second. Okay, so for that we need to start with a discussion of dynamical systems. Right. So what is a dynamical system? It's a system in which the states constantly change with time. Okay. So suppose the state is n-dimensional. So x1, x2, x3, and n variables. All these variables are variables, they're functions of time. So they keep varying with time. And you express the relationship between the state variable and time by a differential equation, which is broadly given like this. So dx by dt is equal to f of x is some function of x. So note that x is a vector, so x is in Rn, n-dimensional Euclidean space, which means dx by dt is also a vector. So it represents a velocity, right? Because rate of change of the state variable, which represents a velocity in n dimensions. And f of x is also a vector function. So for example, if x is two-dimensional, so let's say x1 and x2, f of x is also two-dimensional because left side is two-dimensional vector. Dx by dt is two-dimensional because it consists of dx1 by dt and dx2 by dt. Therefore, f of x is also two-dimensional. Now, this kind of a equation, where do you need it in brain? So you can describe brain as a dynamical system at multiple levels. Even if you look at a single neuron, take for example the Hodgkin-Exley model that we discussed yesterday. It has four variables, right? The voltage variable Vm and the gating variables M, H, and N. So it's a four-dimensional system. That's your X vector in general, if you want to express it in this format. So therefore, what we had yesterday was dx by dt is equal to f of x. F consists of very complicated set of functions, and x has the four components, right? So Hodgkin-Exley model is a special case of this very general dynamical systems formulation where x is four-dimensional. Similarly, in principle, you can express the whole brain as a dynamical system where x is a very large number, because if you think of the state of each neuron, let's say the voltage of each neuron, Vm, so Vm of I of each neuron as a state variable, then you have 100 billion neurons, so it will be a 100 billion dimensional state space. And you have to explain how all these variables vary with time. Okay, so in principle, you can think of the brain at multiple levels as dynamical system. Now, how do you describe this? So first of all, we need to get used to familiarize also with certain concepts. Uh, so what is happening here is at this equation dx by dt is equal to f of x is basically linking the velocity of a point that at every so there is a state of the system is a point in the state space. That point is moving through the state space, So at every point in state space, this equation defines a velocity because it's relating left side is velocity, and you see the right side is a function of the state vector. So it is saying, given a point in the state space, what is the velocity? In which direction the system will move next, right? And to what extent? Velocity has both direction and magnitude. So at any given point, it tells you, this equation tells you what is the direction in which the system will move from now on, and to what extent, to what magnitude. So therefore, you can describe the entire state space using a bunch of vectors. So here on the left, you see a depiction of this vector field. So in general, a state space can be n-dimensional, but imagine for sake of illustration, it's a two-dimensional system. There are only two state variables, x1, x2. Then at any given point in the state space, I can draw a small, small arrow depicting that vector. So that gives you the vector field. The only thing is, imagine that this is happening at, we are depicting at every point in state space and not just a bunch of discrete points. Okay, so the dynamical system that describes the state space basically gives you a vector field. So that's a basic understanding. Now, how do you proceed to analyze such a vector field, such an equation, and right? Basically, what we have to ultimately be able to do is, if I give you an initial condition, that is, if I start from some point in the state space, how will I go? What will be my trajectory? How will I evolve from there? Right? That's the big question. It's a very hard question because if you are given some general dynamical system equations like this, it's very hard to solve them explicitly and find the trajectory. So what people do is start with simple situation, ask simple questions, and then slowly work towards that much larger question of how to compute the entire trajectory starting from some initial condition. So the first step in that direction is finding out what are called fixed points. That is, so you see that in this vector field at various points, you have, at every point you have a vector, right? And vector has some direction and magnitude. But you see on the left side, you can see that somewhere in the top right middle, right, the vectors are of almost zero length. Okay. So Kavin, somebody is asking for admission. I think you need to admit them.
Yes, sir.
You need to be allowed. They constantly, these requests are coming. Okay, so on the left side, you see this vector field, and so at some points, the vector length is 0. That means if you go to that point, or if that point is your starting point, since the vector length is 0, you cannot move from there. You don't move from there. You just stay there forever. Such points typically exist in dynamical systems. They go by different names. Sometimes they're called stationary points. Sometimes they're called fixed points. They all mean the same thing. So we'll use the terminology of fixed points. So on the right side, you see certain fixed points. You see that, so there are 4 examples of fixed points. So there is one in the left top where, the vectors are, they go towards a fixed point from all directions. At that point, vector is 0, but if you go to the neighborhood, then the vector field is pointing towards a fixed point. Same thing is happening in the right top also. Only thing is, the vectors seem to be going outwards from the fixed point. Also, there is a kind of a rotation. They're not going outwards in straight trajectories, but they're rotating around those fixed points. Then similarly, in the bottom also on the left, you see kind of it's a fixed point, which is where in the neighborhood of the fixed point, the flow pattern is slightly weird, right? And let me just 1 second. Right on the right side also, the flow pattern is even more strange because in one horizontal direction, the flow is outwards. In kind of not vertical, but at an angle, the flow is inwards. Okay, so whatever be the flow around the fixed point, at the fixed point, by definition, the vector direction is 0. So once you start from there, you stay there forever. So before you set out to understand the entire vector field and what is the shape of the vector field, what is the pattern, you first identify these fixed points, because fixed points act like some kind of milestones or landmarks. Because if you go to, let us say, a new place, let's say you visit IIT campus. First thing you will find out is what are the major junctions, right? For example, in IT campus, when you enter, right in the beginning, there is a fork where you have to take a left road or a right road. Depending upon where you want to go, take one of those roads. Then actually these two roads meet again after some distance in a big junction called Gajendra Circle. So if you want to know the campus, you have to know these major landmarks. So where is Gajendra Circle? What are the in-gates? What are the out-gates? Right, and that gives you overall layout. After that, you get into more details. The first thing you do is find these junctions. So think of these fixed points as those kinds of junctions. So first, you need to find out where all do you have fixed points in the vector field. After that, next step is you try to find out the flow. Flow means a pattern of velocities, right, and around the fixed point, and slowly to expand outwards and try to find out what is a vector field like everywhere in the state space. So that's how you proceed with the analysis of a dynamical system. So dynamical system, like I said, is given by in this general form like this: dx by t is equal to f of x. X is a n-dimensional vector. So so first thing you need to find out is these points called fixed points, also called stationary points, also called critical points, equilibrium points. They go by, in physics, they are sometimes called equilibrium points, but they all mean the same thing, exact same thing mathematically. It means at that point vector length is zero, which means dx by dt is equal to zero. Remember, it's a zero vector. It's not zero as a scalar because x is a vector. dx by dt is also a vector. And assume that it happens at some point in state space given by x is equal to xs. Okay, so that's a stationary point. So now what you do is we linearize this function around x. I'll explain that in detail later when we get to phase plane. But just bear with me that if you just linearize this f of x around the point xx, then you can convert this kind of a nonlinear equation into a linear equation like this: dx by t is equal to ax. So basically, just as we have a nonlinear function, you can approximate it by a straight line in a small neighborhood, right? Using first derivative. Similarly, you can approximate this f of x by a linear transformation around the neighborhood of this state space, this stationary point xs. So then what happens is the derivative will be a matrix, right? So instead of the nonlinear function f of x, we'll have a linear function a times x. A is a square matrix. Therefore, in that neighborhood of a stationary point, just you see that little diagram out on the top. In the neighborhood of the stationary point, you approximate this dynamical system, which is nonlinear, the original one, by a linear dynamical system, which is shown here. dx by t is equal to ax. A is a square matrix. So what this means is x is a vector, so x is also a vector, and A is n by n square matrix. So this is actually a vector equation. If you split it into the component equations, it looks something like this. Let's say A consists of matrix elements aij, small aij. Then x is a vector, so you split it into all its n components. You have n velocities. All right, so x1 dot is equal to a11 x1 plus a12 x2, etc., etc. x2 dot is equal to a21 x1 plus a22 x2, and so on and so forth. Okay, so like that you get an expansion, right, which is shown here also. It has n vector equations. Now, how do you solve this? Because I mean, if you have a single equation, dx by dt is equal to x, it's simple. So like this. When you have a vector equation, then how do you solve it? So let us start with the simple single equation, single variable. So that is n equal to 1. Then the system of equations will be simply dx by dt is equal to ax, where a is a scalar. So how do you solve it? This is very simple. You all know this. The solution is xt is equal to c into some constant c into e power at. And with this, you can easily check that it satisfies the above equation, because if you substitute in the equation, you get dx by dt is equal to a times c times e power at. So which means c into e power at is xt. So plug it in here, you get dx by dt is equal to ax. So that's how so you can verify easily that it satisfies the equation. Okay, so and you can easily also verify that c is equal to x of 0, which means c is the initial condition, the value of x at time t equal to 0. So this is very simple to solve. So similarly, just I have to just make an assumption because it takes some time to differentiate to derive this. For general case where n is greater than 1, right? This a solution x of t will be of this form. Instead of just c into e power at, it will be c1 into e power lambda 1t times q1 plus etc. etc. So finally, the last term is cn into e power lambda n t times qn. Now, what are these lambdas and qn's or lambdas and q's? Right? These are the eigenvalues and eigenvectors of A. So A is a matrix, right? So you know eigenvalues and eigenvectors, I suppose. So value equation of A will be like this. AQI is equal to lambda AQI. So the QIs are the eigenvectors and the lambdas are the eigenvalues. So you express solution in terms of eigenvalues and eigenvectors. So actually, this is a very good application of eigenvalues, eigenvectors, because I'm sure when you are doing matrix algebra in your high school, when you did eigenvalues, eigenvectors, you might always be wondering what is the use of all this? Why do you have to study eigenvalues, eigenvectors? So this is a very good application. Because if you have a linear dynamical system like this, dx by t is equal to ax, the solution is expressed in terms of eigenvalues and eigenvectors. Why is the solution correct? Right? You can easily verify it by substituting back into the original into this equation. So how do you do that? Just calculate the derivative dx by t of this. So if you do that, you get dx dot is equal to sigma ci. So lambda is in the exponent, right? So that comes out lambda I times e power lambda it times qi. So this becomes ci into e power lambda it times so lambda iqi is equal to aqi. This we know from the eigenvalue equation. This we know this even before, right? Right. So if you substitute this, lambda iqi here becomes aqi, and since a is the common factor to all these terms, a comes out, and you get sigma ci e power lambda it times qi. So this expression sigma ci e power lambda it times qi is nothing but x of t itself. That's the assumption that we made initially. So if you substitute that in here, you get axt. So x dot is equal to xt. So basically, we have shown that this entire expansion is the solution for this dynamical system, the linear dynamical system. Okay, so and there we this derivation, this proof, we made use of the point that the lambdas and q's are the eigenvalues or eigenvectors of A. Okay, so that's how it comes. So now we want to know where are the fixed points and what is the behavioral system around the fixed point. So to understand this, since it will be nice to look at some illustrations, not just look at abstract mathematical expressions. We'll take two-dimensional dynamical systems, but note that for linear systems, it naturally extends to any dimension. There's no problem of generalization. But just for the sake of illustrative convenience, I'll use 2 dimensions. So n is equal to 2. Then x of t is given by c1 e power lambda 1 t times q1 plus c2 e power lambda 2 t times q2. I also make some assumptions that q1 and q2 are orthogonal. Not necessary, but we'll just assume that for this simplicity. So then what are the so what do we understand by the solution? Right, x1t is equal to c1 into e power lambda 1 t. And so basically q1 and q2 are orthogonal vectors. So think of them as two bases, right? X of t is expressed. So c1 into e power lambda 1 t and c2 into e power lambda 2 t are scalars. Q1 and Q2 are vectors. So which means what? You are expressing this as some, like, let's say B1 Q1 plus B2 Q2, where B1 and B2 are scalar. So it's a weighted sum of two vectors, which means you can think of a Q1 and Q2 as a basis for xt. And the weight of the weightage of this, the vectors in this basis is given by C1 into e power lambda 1 t and C2 into e power lambda 2 t. So now this x1t is one component, x2 is another component. But these two components vary with time, like this, two expressions, c1 into e power this thing and c2 into e power this thing. So now we want to see how does this variation look. So what we're trying to understand is, okay, there is a point x, which is x equal to 0, which is a fixed point. So by the way, you can easily see that what is the fixed point of the system? When x equal to 0, the dxdt is equal to 0. So 0 origin is a fixed point. Okay, it's very simple in this case. So now we are trying to understand what is the behavior of the system around the origin, in the neighborhood of the origin. At the origin, it's simple, it just stays put, it's a fixed point. So now you see that x1 is varying like this, x2 is varying like this. Now what happens? Now it all depends on how the variation, how it looks, depends upon the values of lambda 1, lambda 2. Let's say lambda 1, lambda 2 are both positive numbers, or both real numbers and negative. Then since exponent is negative, then both these terms simply go down to 0 at infinity. So which means the both components, right, x1 and x2 go to 0, that means go to origin. That means all these arrows from every direction, they point towards the origin. So all the flow gets concentrated towards the origin. Okay, and that kind of a point is called a stable node. It is stable because the point origin is a fixed point. We want to know whether it's stable or not. What does that mean? If I perturb the system from the fixed point, what happens? Will it come back to the fixed point, or will it just run away from there? If it runs away from there, then we call it an unstable fixed point. If it comes back to the fixed point, then you say it's stable. It's like a marble in a bowl, right? If it is a bowl and they put a marble, it will go down to the bottom and stabilize there. So it's that point is stable. But if you put a marble on top of a hill, then if you put it exactly on top of a hill, it will stay there forever. But if you disturb it a little, it will roll away. So that point is unstable. Okay, so stability is very important to understand the nature of a fixed point. Then it's called a node. I'll tell you why. Because here the eigenvalues are real values, and in principle they can be complex numbers also. And when they have real values, they simply straight away go towards the origin without any circulating movement. When you have complex numbers, you'll have a more circulating movement, as you will see very soon. So therefore, to distinguish the pattern from that kind of circulating movement, you call these points nodes. Now, again, you take eigenvalues are real, but they're positive. Then you see that x1t is given by c1 t per lambda 1t. Lambda 1 is positive. That means exponent will blow up. At infinity, it will blow up. So which means x1, x2 will go off to infinity, right? Which means they move away from the origin. So when you are at the origin, you stay there forever. But when you move away when you even get perturbed off that origin a little bit, then you keep moving away from the origin and go off to infinity. So this kind of a point is an unstable point. Since eigenvalues are real, it's called unstable node. Now you have an even stranger combination that's possible. So previous two cases, both eigenvalues are real, or both are real, but both are positive or both are negative. But what happens if one of them is positive and other is negative? So x1t is c1 and e power lambda 1t, x2t is. So let us say lambda 1 is positive, lambda 2 is negative, which then what happens is x1t blows up because e power lambda 1t goes up to infinity. Then lambda 2 is negative, so e power lambda 2t goes to 0 with that infinity. So x2 goes to 0. So x1 goes to infinity, x2 goes to 0. What does that look like in this plot? X-axis is x1, y-axis is x2. So that means all the points go towards x-axis and go up to infinity, and the y component goes to 0. The x2 component goes to 0. So that's how the flow looks. It looks very strange. In the first quadrant, all the flow goes towards the positive x-axis, and y-axis goes to 0. In the second quadrant, all flow goes towards negative x-axis, y goes to 0. So you see, because of this, what happens is the origin is still the fixed point. But if you start exactly on the y-axis, you'll go towards the origin, both from plus y-axis and minus y-axis. Whereas if you start on the x-axis, you simply go. If you start on the positive x-axis, you go to the plus infinity, and if you start on the negative x-axis, you go to minus infinity in the x direction. That kind of a point is called a saddle node. It's still a node because the eigenvalues are real, but it's called a saddle. So like I said, eigenvalues can in principle be complex numbers, because if you take the eigenvalues of a square matrix, they can be complex numbers also. So when that happens, x1 and x2 will have a more complicated expression. Right, x1 is this. So it will have a real, like a exponential part and a cosine part because of the complex number. So therefore, what happens is in the previous cases, x1, x2 simply were either decaying exponentially to 0 or rising exponentially to infinity. Now what happens is because of the cosine term, cos omega t term, it doesn't decay or blow off to infinity, continuously. It will oscillate. It will show ringing. So because of this, if you plot x1 against x2, like what you see in the left, you will see the the trajectory of the system showing a circulating motion. Okay, so the real part, sigma, right? You see that's e power sigma t. If the sigma is negative, then e power sigma t goes to 0. But then it becomes a decaying cosine, right? A decaying sinusoid. So when when that is true with both x1, x2, then the flow uh, approaches the origin in a circulating fashion. So like you see here, this kind of a point is called a stable focus. It's stable because if you get kicked off the fixed point, you will come back to the fixed point. But you approach it with a circulating motion, and that's called a focus. That kind of a point is called a focus. So it's a stable focus. Now, this sigma, that is the real part, if it is positive, then it will blow up because the e power lambda sigma t, if it is sigma is positive, it will blow up. So then instead of coming back to the origin, it will keep going away from the origin, following a circulating path. That kind of a point is unstable. Then it's called unstable focus. Now we have seen what happens when lambdas are positive, when lambdas are real, lambdas are complex. We have one more special case where lambdas are complex, but they are purely imaginary. Real part is 0. Then what happens? So then what happens is when the real part is 0, like in this case, that means the c power sigma t. Sigma is 0, right? Lambda is sigma plus I omega. So sigma is 0, which means lambda is purely I plus or minus I omega. Then what happens is this exponential part in this x of t term is not there. It becomes 1. So you only have two cosines with some phase difference. So cos of omega t plus phi 1, cos of omega t plus phi 2. So you have two cosines with some phase difference. So x1t is a cosine, x2t is a cosine. If you plot one cosine against the other with some phase difference, what do you get? You get a circle. Okay, so you see already you are getting oscillations. And one of our objective is to construct mathematical models which show oscillations, because I want to construct a deep oscillatory neural network. But that means the neurons have to produce oscillations, and this is a very simple way to produce oscillations. In fact, this is not even probably new to you, because in your high school, all of you must have done the simple harmonic motion of a pendulum, right? So you basically had the pendulum equation is shown here in the bottom. It looks simple SHM, right? Simple harmonic motion. It looks something like x double dot is equal to minus x. Okay. So this is second order equation which you all must have solved in your high school. The same equation can be expressed as two first order equations. See it at the top. x1 dot is equal to x2, x2 dot is equal to minus x1. So if you combine these two equations you combine these two first order equations into single second order equation, you get this. x1 double dot plus x1 is equal to 0. This is your simple harmonic motion equation. The solution is a cosine or a sinusoid. So if you look at this first set of equations, x1 dot equal to x2 and x2 dot is equal to minus x1, I can write this in matrix form like this, what you see in the right top. Okay, so the matrix will be 0, 1, minus 1, 0. Okay, so now what is special about this equation, this matrix? So solve the eigenvalues of this, you get lambda is equal to plus or minus I. Right, and x1 dot is equal to this, and right. So the eigenvalues will be purely imaginary. Okay, that's when you have this kind of circulating motion. It doesn't collapse to origin, it will keep on circulating. Right, it shows oscillations. There's one more case where one of the eigenvalues is 0, other eigenvalues, right, whatever it is. So then what happens is, so x1t is equal to c1 and e power lambda 1t. So the lambda 1 is 0, so it's equal to c1. So x1 is constant, x2 has a time variation. All right, so which means there is only variation in x2 dimension and there's no change in x1 at all. So in all these cases, you had origin acting as an attractor or a repeller. If it is a stable point, then origin attracts all the flow towards it. If it's an unstable point, origin repels the flow, right? We've seen in 2 cases. But in all those cases, both eigenvalues are real or complex, but they're all non-zero. But if one of the eigenvalues is 0, something strange happens. The entire line becomes either attracting or repelling. Because in this case, see that x1t is constant. Okay, so there's no motion in the x1 direction. All motion is only x2 direction. That means now in x2 lambda 2, if it is negative, then x2 goes to 0, but x1 remains constant. So no matter where you start on the x-axis, right, if you have some non-zero y value, you will simply go towards x-axis. So entire x-axis act like an attractor. That kind of a thing is called line of fixed point, so line of attractor. So with this background, I want to solve a simple fun problem. Generally, youngsters like this problem. Okay, it's called the Romeo-Juliet problem. So in this problem, Romeo is in love with Juliet, but so thing is, but they have very strange chemistry between them. If Romeo loves her, like more and more, if Romeo expresses his love more and more, and Juliet gets put off and wants to run away and hide. But when Romeo gets discouraged and starts backing off, then Juliet finds him attractive and goes towards him. Okay, this is how they behave. They're very strange dynamics. Now, can you express this mathematically and write down the dynamical system for it? So it's not very hard. Let us say the state variable for Romeo is R and state variable for Juliet is J. So Romeo is very simple. If Juliet shows interest, he gets excited. Okay, so that his state rate of change of state of R, R dot is equal to A times J. Simple proportionality, and A is a positive number. With Juliet, it's other way around. If Romeo is too excited, she gets put off. Okay, whereas if R is discouraged and aloof, then Juliet gets excited. So how do you express that? J dot is equal to minus B times R, where B is a positive number. So her response is negative to R. So if you write down the matrix for this, A is equal to 0, A minus B 0. So the eigenvalues of this will be purely imaginary. And therefore, if you solve for this, this kind of point is called a center, as we have just seen. In case of center, there's simply oscillation. It doesn't settle down. So like that, in these two fellows also, they don't settle down. They keep chasing each other, constantly going in circles. It's just a fun problem. It is given in the textbook of dynamical systems called, written by Stephen Strogatz. Okay, if you want to take a look at that book. Okay, with this basis, now we are ready to look at what is called a phase plane. Because the neuron models, oscillator neuron models, which we'll be discussing soon, they're all two variable models. I'm sure you have done first day afternoon. You must have looked at what is a Fujinagumo model, what is a Morris-Lecar model, and all that. They're all two variable models which can express oscillations. But if you want to understand how those oscillations emerge, you need to understand all this phase plane. So until now, we have set up laid out some basic ideas about the behavior of a linear dynamical system in 2 dimensions. Now we'll go to nonlinear system. Just okay, so we saw that initially we saw that we began with a nonlinear system, dx by d is equal to f of x. And then I said, okay, let's linearize this around some fixed point, and then you get, instead of f of x, I have ax, right? I replaced the nonlinear function f of x with a linear expression a of x, a times x. I didn't elaborate exactly how that is done, so now I'm going to show it in this 2-dimensional case. So phase plane is basically the state space of a dynamical system when the number of variables is only 2. Okay, so it's easy to analyze dynamical systems in 2 dimensions, especially nonlinear ones. The high-dimensional nonlinear systems are very hard to analyze. You cannot, for example, come up with a general analytic solution for such problems. There's a lot of things that can be done in 2 dimensions. And if you want oscillators, 2 variables are enough, right? Two variable dynamical systems are enough to produce oscillations. There's a lot of elegant theory that gets developed. So all that is called phase plane analysis. The study of 2-dimensional dynamical systems is called H-plane analysis. So if you want to study a 2D dynamical system, then you can write it in more general terms. I've just said x dot is equal to f of x, where x is a vector. But if you have only 2 dimensions, then it's more convenient to write down the individual equations. So we'll write it as x dot is equal to f of x comma y dot is equal to g of x comma y, where x and y are the 2 state variables. Okay, so now how do you proceed to analyze this? Like I said, in general, it's very hard to, if I give some random f of x comma y and random g of x comma y, it's very hard to solve them. So what we first do is, we don't directly solve them. Like what we have done earlier, we first find out the fixed points. In case of the linear dynamical system, x dot is equal to x, fixed point is very simple, x equal to 0 is the fixed point. Whereas with nonlinear systems, that's not the case. X equal to y equal to 0, that's not necessarily a fixed point for this system. So you need to find out what are the fixed points. So for that, how do you do? Fixed point is a point where x dot is equal to 0, y dot is equal to 0. So which means you see that equation at the top, x dot equal to f of x comma y equal to 0, y dot equal to g of x comma y equal to 0. So you need to solve both these equations. So the very point of studying all this in 2 dimensions is the ability to draw some pictures, make some illustration, right? It's easy to visualize what is happening in 2 dimensions. In 3D, it's already very hard, and high dimension is impossible. So what we do is let us solve these equations pictorially and see what it looks like. So for that, we first draw the f of x comma y equal to 0, right? That's actually a curve in 2 dimensions, right? So you see that this curve is f of x comma y equal to 0. And this curve is called x null cline. That's the terminology. Null means 0, cline is a curve. It's kind of a 0 curve for x, right? This is a curve on which x dot is equal to 0. So on this point, there's no flow in the x direction, all flow is in the vertical direction. That's what it means. Similarly, if you take the second equation, g of x comma y equal to 0, this is also another curve. And obviously, you can imagine, you can guess that this curve will be called y null cline or YNC. It looks like this. Now we want to find fixed points. What are fixed points? Fixed points are points where x dot equals 0 and y dot equals 0 simultaneously. That means f of x comma y equal to 0, g of x comma y equal to 0 simultaneously, which means in graphical terms, these are points where these two curves intersect. Okay, so in this example, these two curves intersect in 2 points. So these two are the fixed points. Now, what did we discuss earlier? So when you have a fixed point, you first find out the fixed point, then linearize the system around the fixed point so that you can find out the behavior of the system around the neighborhood of the fixed point. Because the linearized version is valid only in a small neighborhood of the fixed point. So we'll study the linear system and then find out what kind of a point is it, because we classified many different kinds of fixed points, right? We said there are stable nodes, unstable nodes, stable focus, unstable focus, saddle, and all these things. So we need to find out what is the behavior of the system around the fixed points. So how do you do that? So let us assume that x dot y dot is a fixed point. Okay, so so if you do that, so f of x dot y dot is equal to 0 by definition because it's a fixed point. Now what we do is you expand this as a Taylor series. Okay, so let us assume that x is equal to x dot plus epsilon x and y is equal to y dot plus epsilon y. We introduce 2 new variables. And so we are now looking at the behavior around the fixed point x naught, y naught. So we define new variables only in the neighborhood of x naught, y naught, and therefore you define x and y like this. Now x dot is equal to f of x comma y, right? Now they expand this as Taylor series. So in your high school mathematics, you might have done Taylor series in one variable. But here we are looking at Taylor series in multiple variables, which looks something like this. So therefore you get x is equal to x naught plus x epsilon x. At the top, you can see that. If I differentiate both sides, you get x dot is equal to epsilon x because x naught is constant. So if you plug it in here, you get epsilon x dot is equal to f of x dot y dot, x naught y naught, plus epsilon x into dou f by dou x plus epsilon y into dou by dou y. You need to use derivatives, right? This is the first order term in the Taylor series. After that, you have higher order terms. We'll ignore them for now because we are only trying to linearize. Now, in this equation, f of x naught y naught is 0 by definition because x naught y naught is a fixed point, and at fixed point f of x comma y is 0. So this becomes 0. Similarly, g of x naught y naught is also 0. So you can get rid of this term and this term. Then higher terms will ignore them because we're only approximating the dynamical system in a small neighborhood of the fixed point. So you get something like this. Okay, so if you do that, then you have a 2 by 2 matrix. The dynamics is expressed as a linear equation, right? So epsilon x, epsilon y, let's call it a vector epsilon. And then this 2 by 2 matrix, it's a Jacobian actually, it's called a Jacobian. We'll use it, denote it by matrix J. All right, so you can express this equation now as a linear equation, a linear dynamical system, epsilon dot is equal to J epsilon. Now we need to find out what is a kind of a fixed point, okay, that this fixed point is, what kind of fixed point is it? So how do you do that? You just find out the eigenvalues of J and that will tell you what kind of fixed point is, because the nature of the fixed point completely depends on the eigenvalues, as we have seen before, right? Now let's take a small example again from the Strogatz textbook to apply all these ideas and find out the stability around the fixed point. So this example, dx by dt is equal to minus x plus x cube. Here dy by dt is equal to minus 2y. So it's conveniently, it's a very simple problem because you have x is independent of y and the two dynamics are totally independent, decoupled. Now, how do you solve this system and find the fixed points? Right, you take the null line is f of x, null line is f of x comma y is equal to 0, which means see that minus x plus x cube is equal to 0, which means that x is equal to 0, 1 or minus 1. So in this case, although it's supposed to be a function of x and y, it's a very simple problem. The expression is actually a function of only x. There's no y here at all. So when you solve it, you get x equal to 0, 1 or minus 1. So therefore, y can be anything. That's what it means. Similarly, for the y null line, g of x y is equal to 0. So this g of x y is only a function of y, no x here. So minus 2y is equal to 0 means y equal to 0. Therefore, x is anything. So what does that mean in graphical terms? X is 0, 1 or minus 1, y is anything. What that means is these three vertical lines. X is 0, y is anything. That means the vertical line going through the origin. X is 1, y is anything. That means the vertical line going through x equal to 1. X is minus 1, y is anything. That means the vertical line going through x is equal to minus 1. So you have three vertical lines. All these three vertical lines represent the x-null lines. Now y equal to 0, x is anything. That's basically the x-axis, because y is 0 on x-axis, x is anything. So this is a very strained set of x and y null points. So look at the intersection points of this. You see the three intersection points here, here, and here. Now the question is, what is their stability like? Right. So let us go to the point at the origin. Right. And so the Jacobian here, if you solve this, you get this. And at origin, if you plug in the x is 0 and y equal to 0, you get a equal to this. And the lambdas are negative. That means it's a real and negative. Therefore, it's a stable node. This point is a stable node. That means all the flow comes towards this point from the neighborhood. Now, if you look at other 2 points, that is plus or minus 1 and 0, that is this is 1, 0 and minus 1, 0. At both these points, you can easily verify that the Jacobian is this matrix. And if you find the eigenvalues, it will be 2 and minus 2. Therefore, it's a saddle node because one of the eigenvalues is positive, other is negative. So which means what? If you can easily work out that flow is outwards in the horizontal direction, x direction, flow is inwards in the vertical or y direction. Okay, so this is saddle node, and if you look at neighborhood, like neighborhood of these points, you see that the flow here is vertical downwards and rightwards. Flow here is downwards and leftwards, right, etc., etc. So now we are able to work out the flow pattern in the neighborhood of these three fixed points. At the fixed point in the center, flow is completely towards the fixed point inwards. That is number 2 fixed point. Fixed point number 3 on the right side. Flow is away from the fixed point in the x direction and towards the fixed point in the y direction. So in this part, it is downward and left. In this part, downward and right. This part is upward and right. Here it's upward and left. Similarly, you have on the left fixed point also. So with this now, we are able to completely reconstruct the vector field, right? If you are anywhere here, flow is completely inwards and towards the origin. If you are anywhere here, flow is towards x-axis but outwards towards x infinity. If you are anywhere here, flow is right outwards, right, but towards x-axis, but again towards the x plus infinity. Okay, so like that you can find out what is going on with a simple two-dimensional system by applying these phase plane techniques. Now I'll just pause here a little bit and see if you have any questions. What happened to the screen? Hello, so I'll switch PPTs here. Do you have any questions?
Hello, sir.
Yeah.
Sir, I have a question. Can you just tell some practical, application where you can apply like this model? Maybe
Yeah.
are we considering it in a angle of a single neuron point of view, or maybe considering it in a network structure also? Can you just
Yeah.
explain?
So thing is, I mean, that's what I'm working towards. Only thing is I'm giving you like all the fundamentals starting from the beginning, because otherwise what will happen is, okay, so right now I began discussing dynamical systems two variables. With this background, I'm going to introduce two variable neuron models, which show oscillations. Okay, so you already looked at them on Monday afternoon, like not
Yeah,
Monday, sorry, Saturday afternoon,
yeah,
but without understanding how they work, right? Because I'm sure you might have just looked at some code, run the code, and see that you have oscillations, right, with the Fujino-Gumo and
yeah.
Morris Leclerc, right? But you are not able to analyze it mathematically to understand why you are seeing oscillations in these models. Because unlike a ReLU neuron or a Magellan-Pitts neuron, which are very simple static functions and nothing much to understand,
Okay.
an oscillating neuron is more difficult to understand. Why does it oscillate?
Yes.
So since say basically in a full semester course, I have a luxury of discussing everything in detail so that there's no doubt. Because the thing is, very often what happens is people read some blogs or watch YouTube videos and get some working knowledge superficially, and you just go on with that. But if you want to do research, that kind of knowledge is not sufficient.
Yes, yes.
You need to go all the way to the bottom to understand every little bit of. Only then you can innovate and come up with new models and things like that. So this workshop, the objective is to help people go to the fundamentals, not just give a superficial working knowledge. Right. And this is only one time thing. Once you do it, you got it, right? It will stay with you forever. So that is what I'm building up towards in this morning session. So phase plane is the basis, phase plane analysis is the basis. Now I will show you how to use phase plane methods to understand limit cycle, means oscillations. A special kind of oscillation, which is what all these neural oscillators are. Right. And then with that background, I will then show how to get limit cycles. Sorry, how to get this neuron oscillator models. So bear with me, I'm getting there. That's exactly what I'm working towards, but it
Okay.
will take some time. There are a lot of
Okay.
steps in between. But
Okay.
please ask questions. If you have doubts,
Uh,
please ask questions.
okay. So we have to maybe you have to think in an angle not as a single neuron, maybe as a collection, right?
No, right
States.
now, all this I'm doing it for a single neuron.
Okay.
At the end of this discussion, I'll describe how a single oscillator neuron works.
Okay. Okay.
Then starting from about 11:45 or so, I will start looking at networks.
Okay.
Okay, there's so much. The moment you look at nonlinear oscillators, it's a pretty complicated topic. And that's how it is. I can't help. Right.
Okay, sir. Thank you.
Any other questions? Okay, like the steps. So somebody said, can you give a simple summary? So basic idea began. So we want to understand something very simple, ultimately very simple. There are these things called neural oscillators. Okay, these are nonlinear systems. I want to understand how do they oscillate? How can you explain that? So to answer that one question, I need all this background. So I began with a general discussion of dynamical systems. What's a dynamical system? Any system in which the state variable changes with time. Oscillator is an example of that. Okay, so and the kind of oscillators that neural oscillators that you will be looking at are all nonlinear systems. So because those kind of oscillations you cannot get in a linear system, you have to have a nonlinear system, which means they are nonlinear dynamical systems. So you need to have some idea of what is a nonlinear dynamical system, and then we looked at some methods to understand them. So general nonlinear dynamical system is an n dimension, which is very hard to analyze. We don't need that to understand neural oscillators. It is enough if you understand what happens in a two-dimensional system, right? So that's what I said. And then I came to a phase plane. Phase plane means a two-dimensional dynamical system. In that, how do you study the dynamics? So I've given some examples and given some theory. With this background now, I will describe how to explain oscillations, right, in a two-variable system in a phase plane. And these peculiar kind of oscillations are called limit cycles. And that's the kind of oscillations that these neural oscillators exhibit. Okay, you need to know all this theory. All this you never see all this in general AI literature because they're very different. It's a completely complementary field, right? And this is the kind of a bridge that you need. This is what you need to make that bridge between uh, like this brain-inspired models and this AI kind of thing. Just I'll get there. Just give me 2 hours and I'll get there. Okay, I'll show you how to construct networks. And afternoon, you'll actually program these networks. I mean, you'll run these networks on various data sets and see what happens. But the theory, even at single oscillator level, is very involved. That's what I'm trying to say. Can't help it. Right. So the sequence is dynamical systems in general, linear dynamical system, nonlinear dynamical system. Linear dynamical system theory is very simple and general. Nonlinear dynamical system theory is very complicated and not general. Right. Therefore, what we do is we stick with only two-dimensional dynamical systems, two-dimensional nonlinear dynamical system. That is what we do with phase plane, because you can draw some pictures and analyze it pictorially. That's the first step. So in phase plane, we look at specific problem of studying oscillation. Right. These are called limit cycle oscillations, and the neural oscillators we'll be looking at from now on. They're all what are called limit cycle oscillators. Okay, and once we understand the math of that, then we are ready to construct networks of such oscillators. So that's the sequence. All this will finish, this theoretical discussion will finish by 1 o'clock. But please stop me because you need to get that big picture. Even if you don't understand all the details of the math and all, I think it'll be good to have that big picture so that you know where to place the idea in the larger context. But please do ask questions. I mean, you happily can interrupt me. Anything else? Any other questions? This is not like a Markov chain. Okay, Markov chain is also a dynamical system, but these are continuous systems and differentiable. So therefore, math is quite different. See, in a discrete dynamical system, you have something like x of t plus 1 is equal to some function of f of x, f of some function of x of t. In a Markov system, you jump from state to state. These are all discrete states. Here, you move continuously in a continuous space, which is described by a differential equation or a set of differential equations. That's the main difference. But both are, there's a state change in both cases. Okay, so let's move on. I mean, as in when you have any doubts, please interrupt and ask. But also, I think I'll speed up a little. Okay, so this is when you talk about neural oscillators, they oscillate, but it's a very special kind of an oscillation. So they are called limit cycles. So what is a limit cycle? First of all, it's a periodic solution. It's a cycle, so it's periodic, which means x of t is equal to x of t plus some capital T, where capital T is a period of the limit cycle. Okay, so it keeps going round and round. And this we will study the limit cycles only in 2 dimensions. We'll stay away from high dimensions from now on. When we talk about single neuron oscillators. So it's a loop, it's a closed loop inside in a plane. So that's your limit cycle. So once you start system anywhere on that loop, it'll keep going round and round in that loop. Okay. Now what is strange about limit cycle is, let's say you have an oscillator going round and round in this loop, and now somewhere in the middle I just kick it off the limit cycle. It gives some perturbation, gives some noise or something, and kick it off the limit cycle. If you kick it off so that it goes outside the limit cycle, then slowly it will again roll inwards towards the limit cycle, approaches the limit cycle asymptotically, and then after that continues to go around in the same cycle. Or if I kick it off the limit cycle inwardly, then again it will come back up and then goes round and round inside the limit cycle. Okay, that's the nature of limit cycle. It is stable in this sense, because we have seen a different kind of stability when it comes to fixed points, right? In case of fixed point, stability means if I start on the fixed point, right, I'll stay there forever. But if I get kicked off the fixed point, I come back to the fixed point. That is the stability of a fixed point. Unstable fixed point means if I get kicked off the limits, kicked off the fixed point, you will go away to infinity. That's instability here. Whereas limit cycle is also stable in a different sense. As long as I am on the limit cycle, I keep going round and round around on that orbit. But if I get kicked off that orbit, I come back to the orbit. This is very important. It's a very special kind of an oscillation. Now, if you look at planetary systems, they are not limit cycles, because if you take a planet, right, going in an orbit and then kick it off the orbit a little bit, suppose a meteor hits it or something, it'll get displaced. After it continue to move in the new orbit, it doesn't come back to the old orbit. Okay, so whereas limit cycle is not like that. It will come back to the same orbit. Now, why do you need this? And why is it? How is it different from the other oscillation that we know? Like, in high school, you have studied simple harmonic motion. That's not a limit cycle. It's oscillation, but it's not a limit cycle. What's the difference? In a simple harmonic motion, right, if you start from anywhere in the state space, if you
Excuse
start,
me, sir.
yeah, please go.
Sir, are you sharing your screen right now?
Ah, God. So can you see now?
Yes, sir. Thank you.
Okay, very good. I'm sorry for pointing about this. Sorry about this. So this is a limit cycle. Okay, if you are on this is in a two-dimensional surface, in a two-dimensional 2D plane. If it's a closed loop in a 2D plane, if you are on that loop, right, you go round and round that loop forever. If you get kicked off the loop outwardly, then you come back inwards and settle in that loop. If you get kicked off the loop inwardly, then again you grow outwards, move outwards, and join the loop, and again keep going in that loop. That's a kind of a oscillation. That's a limit cycle. That basically it's a limit of a cycle. That's a limit of the flow. That's why it's called a limit cycle. It's also stable in a different sense, because if you look at the fixed point, right, if you get kicked off the fixed point, which is, then it'll come, you go back to the fixed point if it is stable. Similarly, here, if you get kicked off this limit cycle, you go back to the limit cycle. Therefore, that kind of limit cycle is called a stable limit cycle. You can also have unstable limit cycles, where if you get kicked off the limit cycle, you'll go away from it. Okay, so that's also there. Right, and this is a very different kind of oscillation compared to a simple harmonic oscillator. Because in a simple harmonic oscillator, if you start close to the origin initially, you'll keep going round and round close to the origin. If you start far away from the origin, you keep going round and round far away from the origin. Right? But you don't change orbit. Whereas in the case of limit cycle, no matter where you start from in the plane, you always go to that fixed point. So if you look at example of a simple harmonic oscillator is a simple pendulum. If the simple pendulum starts at close to the vertical, then it will make only a small oscillation. If you pull it very far from the vertical and then let it go, then it will make big oscillations, right? So it's not a limit cycle. The limit cycle, you always go to the same amplitude. Why is it important to model a neuron? Okay, look at this. This is the spike pattern of a single neuron. Now, suppose you disturb the spike pattern by injecting some brief current, okay? Then what will happen is there is a transient deviation from this pattern, right? So maybe the first spike or this might be transiently high. After a couple of spikes, it will come back to the same amplitude and goes off at the same amplitude, right? So any disturbance will not linger. The oscillation will come back to the same standard amplitude. Okay, that's the kind of thing you see in the neurons, right? That's exactly a limit cycle kind of oscillation. A simple harmonic oscillator will not give you that behavior. Therefore, if you want to model neural oscillations, you need limit cycle kind of oscillation and not simple harmonic oscillator kind of oscillation. So this is the important point. Is this clear? Okay, now the question is, how do you create such oscillators? So I'll just give a couple of examples and try not to go deep into this theory. So let me take this in. Yeah.
Sorry. Sir, what would perturb the neuron?
So if I have a neuron just firing away, right,
Is it
and I can poke an electrode into the neuron and then inject some brief current pulse. That will perturb the voltage, right?
So would something like from a clinical point of view, would something like epilepsy?
No, so epilepsy is
no.
happening first of all at the whole brain level.
Yes.
Right. Here I'm talking about a single neuron.
Okay.
Because if a single neuron, let's say take a neuron which is showing regular spiking. Okay, regular spiking means the spike pattern, spike frequency is uniform. So that's like a limit cycle. Right, you're going exactly round and round in the same periodic.
Okay, so on experimental level, when we do experiments, we want to perturb the activity of a single neuron.
Yeah.
Okay. I got that. Thank you.
How will you do that? By injecting current briefly.
Right, definitely. Yeah.
Then
so that is when we use, okay.
So if the neuron is like a simple harmonic oscillator, then when you inject current briefly, there's a transient rise in amplitude, but that will continue, that will persist forever. If it is a simple harmonic oscillator kind of an oscillator. Whereas that's not the case with the real neuron. It will come back to the same action potential amplitude. Right? Like in case of a limit cycle. That's why you need to understand the limit cycle theory.
Yes, sir. Thank you, sir. Thank you.
Okay, thank you. So let us take yeah, please go ahead.
Yes, sir, I wasn't able to get it how neural spiking activity can be modeled as a limit cycle.
Okay, first of all, in limit cycle, I have two variables, right? Because it's an oscillation in a plane. In case of a neural spiking, we only talk about the voltage variable. But you have seen in the examples that we saw on the first day that there are more variables. You are not showing them, but they are there in the background. Right?
Yes, sir. Yes,
so if you look at Hodge-Nexley, there are 4 variables. If you look at Fujii-Nagumo, there are 2 variables. Okay, if you only look at the voltage, it look like the spike pattern, but there's also a second variable, which you may or may not be looking at all the time, but it's there. Right? So if you look at the flow of the system in 2 dimensions, if you superimpose, if you plot v of t against a second variable, let's say some n of t or something, that will look like a closed loop in 2 dimensions, right? If you plot v of t as a function of time, it will look like this. But suppose there is there is a second variable in the neuron, like some gating variable. If you plot one against the other in v and m space or something, then you'll get a closed loop. It'll just keep going round and round like this. Like this. Right? Okay. You can visualize that. I'm saying that is a limit cycle because when you perturb it by injecting some current, you briefly get kicked off that loop, but after some time you'll settle back on in that loop because amplitude comes back to the same value. It's a very subtle difference, but quite important because somehow the molecular machine of neuron is takes so much trouble to get back to that standard amplitude. Okay.
Okay.
So how do you
So,
get
yeah,
that?
yeah.
What kind of equations will give you that kind of behavior, which is very different from simple harmonic motion? So for that, we look at a very simple example, which is a Hopf oscillator. Right. So
Okay.
so the equations look
Mhm.
like this: x dot is equal to minus y plus mu x into 1 minus x square minus y square. Y dot is equal to plus x plus mu y times 1 minus x square minus y square. Okay, so this is how it looks. You can see that it's a cubic nonlinearity. Simple harmonic motion is only linear. This right? Where is this? It's linear. Okay, whereas here it is a
Mhm.
cubic nonlinearity and looks very complicated. But actually, it's not very complicated if you do a little bit of variable transformation. How do you do that? Just express this in Cartesian coordinates, right? X and y. Express it in polar coordinates. So x is equal to r cos theta, y equal to r sin theta. So when you do that, what happens is these equations, there's a bit of algebra, but if you do all that, these equations simply reduce to this. This is for the r dimension, and where is the theta dimension? Theta is this. So if your dynamics in r and theta will look like this. In r dimension, it is dr by dt is equal to mu r into 1 minus r squared. For theta, it is theta dot is equal to 1. Okay, what is so complicated in x1, x and y dimensions? Looks so simple in r and theta terms. Now let us try to understand what's going on with this r and theta. Okay, so the r dynamics is like this, and also in this case, x and y are completely coupled. The x dynamics has both x and y in it. Y dimension also, y dynamics also has x and y in it. So it's very complicated. Looks very complicated. But once you make this substitution and transform to polar coordinates, r dynamics simply is a function of r alone, and theta dynamics is simply a function of theta. Not even theta; it's a constant. Okay, let us interpret what it means. So dr by dt is equal to mu r into 1 minus r square. So see what happens. So if r initial value of r is less than 1, right side is positive. That means dr by dt is positive, which means r increases. Right. So now if initial r is greater than 1, then 1 minus r square is negative. So right side is negative, which means dr by dt is negative, which means r goes down, r decreases. See what is happening is, no matter what r, if r is less than 1, it will go towards 1. If r is greater than 1, it will come down towards 1. If r is equal to 1, it stays put, no change, because right side is 0. So in this equation, r simply always goes towards 1, no matter where you start. Okay, and then theta dot is equal to 1, which means the angular velocity is a constant. Now, if you superimpose both of them and draw pictorially, you get something like this. Right? And no matter where you start in the phase plane, you will always, r will keep going towards 1, no matter where you start. And theta will simply go round and round. Theta dot is equal to 1. So it's simply a rotor. Right? Now, that's a beautiful limit cycle. Right? And this is very different from SHM. In SHM, no matter where you start from, it will go in circle which goes to that point. If initially you are far off from origin, you make a big circle forever. Initially it's close to origin, you make a small circle forever. Whereas here, see what happens because of this equations, these two equations. No matter where you start from, you'll always go to a circle of radius r equal to 1, the unit circle. And the rotational motion is constant, theta is equal to 1. That's an example of a limit cycle. So this is the kind of a behavior we want in neural oscillators. And the Hopf oscillator is the simplest example of this kind. There are more, they're slightly harder to analyze, but Hopf is a great example of how you can construct a limit cycle. Now, it so happens that so the same equation can also be expressed in terms of complex numbers, right? So two variables, right, x and y. You can combine the two variables into a complex number, z equal to x plus iy. Then it so happens that you can write these two equations in terms of a single complex equation, which looks like this at the top. dz by dt is equal to I omega z plus 1 minus mod z square times z. Now, how do you know that this and the first equation are both the same? Very easy to show. Let us express z as in polar coordinates like this. Z is equal to r into e power I theta. If you plug it in and do some reduction, you get this, And if you separate real part, imaginary part, you get this d by dt is equal to 1 minus r square into r, and d theta by dt is equal to omega. So exact same thing, right? So you can write this in complex number terms, and that we do that because it's very convenient. So if you want to construct these networks, this is very convenient, right? So a simple example of limit cycle. So what I will do is I'll skip all this, go to a separate thing, and show how you get limit cycles in more complicated cases. I'll just give you the concept without going deep into mathematics. I think people are finding it somewhat, too involved. So I'll just give the high level picture. So let me take a simple dynamical system like this. dx by dt is equal to this, dy by dt is equal to this. Then I want to understand the flow everywhere in the phase plane without actually solving and calculating the flows. How do you do that? Take the external line. This is equal to 0. So dx by dt is equal to 0, which means x minus y equal to 0. That is the straight line. Now on this line, x minus y is equal to 0. That's x dot equal to 0. Now what happens if I go above this line? Right? If I go above this line, what that means is I'm increasing y. That means x minus y is 0 on this line. But if y is increased, right, then x minus y here will be negative. Okay, so which means x dot is negative above this line. So above this line means this entire thing. X dot is negative. Therefore, contrarily, if I go below the line, x dot will be positive. So x dot is positive here and here. Similarly, if you take this y null line, dy by dt is equal to x plus y. That x plus y equal to 0 is this straight line. If I go above this line, that means y is increased further, so it will be positive. So y dot is positive here and here, and y dot is negative here and here. So if you summarize this, what I'm getting is the flow in this quadrant is like this. X dot is negative, that is goes leftwards. Y dot is positive, goes upwards. So arrow points like this. So in this case, in this side, arrow is x dot is negative, y dot is negative. That means arrow points leftwards and downwards. Here, x dot is positive, y dot is negative, which means arrow points rightwards and downwards. Here, x dot is positive, y dot is positive, which means arrow points rightwards and upwards. So what I'm trying to say is, you can get the overall flow pattern in the vector field without actually calculating the flow vector at every point. That is important because, so what we'll do is, okay, I'll skip this theorem and all, but I'll go to the oscillator model that we looked at before. So what happens is, you will find that you'll have a limit cycle around a certain unstable focus. So I'll come to that later. So now we have seen Fujinoguma model before, right? So it's actually constructed by simplifying the Hodgson-Huxley model. So this is a Hodgson-Huxley model which has 4 variables. Okay, and how do we simplify it? We assume that m is a fast variable, so which means m d by dt is equal to 0 all the time. So it quickly goes to 0, right? So I will set this to 0. If this is set to 0, the right side is minus m plus m infinity. Okay, so therefore m is equal to m infinity all the time, but I'll assume that. If I can get rid of this differential equation, then I also assume that h is a slow variable. That means I doesn't vary much. So I'll assume it's approximated by a constant h equal to h naught. By doing that, I got rid of h dynamics also. So then I only have dynamics for Vm equation, this one, and n equation. These two I got rid of, equations I got rid of. So then I'll have only 2 differential equations. Therefore, I can use phase plane. So there is some more transformation simplification that are done. When you do that, you can reduce the 4 variable Hodgson-Huxley model to a 2 variable system like this. dv by dt is equal to f of v minus w plus im. W is a new second variable. And fv is a nonlinear cubic function given by this. And dw by dt is given by bv minus rw, where b and r are small positive numbers. Okay, so this is Fujinoguma. So when you draw the null lines for the first equation, that is the V null line, this one, this if you set to 0, it will look like this, like some kind of inverted N-shaped null line. For the second equation, if you set this to 0, you get BV is equal to RW, or V is equal to RW by, or W is equal to BV by R. That's a straight line. So you get a straight line. Those are two null lines, right? So now what happens is, as you vary the input current is this quantity IA, or applied current IA. So what happens is, in this equation, this IA or IM, whatever it is, right? As you keep increasing the input current, this null line keeps going up, right? Because it comes, I comes as a additive constant, on the right side. So when you do that, what happens is, for I equal to 0, to show you the phase plane how it looks. For I equal to 0, right, these two curves intersect here at this point. And if you do the stability analysis of that, you'll find that it's a fixed point. It says stable fixed point. Therefore, no matter where you start from, you come back to this point, okay? And that's like your resting state, right? You can work out the math and all that. You can show that it's a stable point, it's like resting state. But if I increase the input current, this V null line starts rising up, so this comes a relative constant. Then what happens is, this will intersect somewhere here like this. Now at this, the intersection point has now moved. Earlier it was here, now it has moved here. At this point, you can verify that it's actually an unstable focus, right? Which means if I start from here, I'll get kicked off. And focus means the circulation around that is it'll have a circulating flow, right? It's not just outwards or just inwards. It's a circulating flow. And because of that, what happens is there'll be a limit cycle around this. You can easily, kind of show that if you simulate the equations. And therefore, in this case, if you simulate the equation, you'll see oscillations. Because at this point, the intersection point, in this case, is an unstable focus. So it doesn't go to that point, it will just oscillate around that point. You get a limit cycle. If you increase the current further, then the intersection point moves here. So for very low current or zero current, intersection point was somewhere here. For intermediate levels of current, intersection point was somewhere here. For much higher current, intersection point is somewhere here. Now, when the intersection point is on this side, then you can again show using some stability analysis that it's a stable fixed point, and then everywhere, wherever you start from, you'll always come here and settle down. So this is like your, in Hodgkin-Huxley model also, you had a case where as you kept increasing current, there are no more oscillation, right? There's only very small oscillation, the action potentials have disappeared. And that's where you said that the curve ends, right? There's no firing output. Okay, so here also you see all those behaviors. For small current, you have resting state. Okay, and for intermediate levels of current, there's oscillation. For high currents, again, it just goes to high voltage and stays there, no oscillation. So all the behaviors that Hodgkin-Huxley model shows, this simple, which is Hodgkin-Huxley is 4-variable and highly nonlinear. This is a very simple model derived from Hodgkin-Huxley, 2-variable model. This also shows some of those qualitative features, right? And here also there's a threshold property. And after the threshold of the current only, you have oscillation. So similarly, let us look at one more variable, one more neuron model. It's actually, this is not a model of a neuron, it's a model of a muscle fiber. And muscles and neurons come from the same family of cells. These are called excitable cells, right? And they are capable of oscillations in principle. So this is a model of barnacle, is a sea creature called barnacle. It's muscle fiber. It has 3 equations, just like Hodgkin-Huxley has 4 equations. This has 3 equations. So you simplify this by making an assumption that the M equation is always settles down. It's a very fast dynamics. So M is equal to M infinity. So if you substitute this, you get only 2 variables like this. And if you draw the phase plot, okay, it will look like this. So again, just like in Fujimoto, you have this N-shaped null line, that is a P null line. And the second null line is corresponds to this W. That looks like this kind of a sigmoid, okay? And again, like the previous case, if the intersection point is here in the first branch, then it's like a fixed point, as like a resting state. It doesn't oscillate. but if the intersection goes to the middle, that's when we'll have an unstable focus here. So the flow doesn't go to the fixed point. It simply oscillates around the fixed point. You get limit cycles. And if you increase current further, the intersection moves to the right side, to the rightmost branch. At that point, again, the intersection point will be a stable point. Therefore, there's no oscillation, and then voltage simply settles down at a constant value. So if you summarize all these three as a function of the input current, the output is like this. Up to this threshold value, there's no oscillation. Output is close to a fixed value. But after this threshold, output will start oscillating between two limits, and that's a limit cycle. Those two limits are shown like this. And after some point, suddenly the oscillations stop, and again you go to fixed point behavior. This is a picture of this thing. So similarly, you can also understand the behavior of the Ezekevich model. We have done the Ezekevich two-variable model, I think, on the first day. Again, same thing. We have N-shaped null. No, we have a quadratic null climb for the first one, and then a linear null climb for the second one. And you have the resetting step, right? And if you simulate that, you get all this rich, diversity of neural firing patterns. Okay, so that's the kind of power of phase plane methods. They can get all these behaviors, and I just hope I gave intuitive understanding of this. So now what I'll do is we'll take a short break, 15-minute break. And if you want to discuss among yourselves, and I'll come back, then you can ask some questions. And after this, now I will start looking at oscillator networks. We'll take this oscillator understanding as a starting point, and we'll discuss how you can construct networks out of it. Any questions? Or you can wait for 15 minutes. Let us meet back at 11:40. Right now time is 11:25, and we'll continue. Okay. Okay, thank you. Oscillators. So with this, now we will see how to construct networks. Okay, so there's some background about my lab. So we know that neurons communicate with each other by exchanging electrical signals. And these signals are in the form of action potentials. We all know this. So because the neural signal is in the form of a series of action potentials, if you ask the question, what is a neural code? How do you mathematically describe it? Right now, there are two popular approaches to it. One says it is in since the spike shape, individual spike shape is pretty much standard. The only information that there is in the spike time. When did the spike occur? So therefore, with that assumption, if you want to describe a series of spikes, you can describe them by a series of delta functions, where the only thing that is indicated is that spike time. So neuron models which produce, this is called a spike code. The other approach is don't worry about the exact times of spikes. Just look at the spike frequency. That means a local time frequency, right? That is a calculated frequency only in a small time window. Then see how it varies, right? And that will gives you like a continuous variable of frequency, right? And this is called a rate code. And all your deep neural network neurons, right, the sigmoid and ReLU, all these are based on the assumption that the information is in the form of a rate. Right, so you have spiking neuron models which produce spikes, and you have rate-coded neuron models which produce say a scalar variable output, which denotes the rate. And all your deep networks is based on rate-coded neuron models. Right, so we have seen all this yesterday. But if you want spiking neurons, we have here also you have seen a whole bunch of neuron models, right? Like leak integrate and fire neuron model, which we have seen yesterday. And Ezekevich neuron, we have seen it. Today also briefly we have seen it. Hodgkin-Huxley, we have seen it already. And if you want even more detailed analysis of single neuron, you can break it up into small components and model each component by analytical circuit. And you can do all that, but we are not interested in that for now. So when you look at this wide array of neuron models, right, it will automatically give rise to an important question, which is what is the right scale at which you need to model a neuron? because you have wide range. On one side, you have extremely simplistic, artificial neuron models, where you talk only in terms of rate. Other side, you have the super detailed models, like biophysical models, where for a single neuron, you can have hundreds of compartments and so on. So what is the right middle ground? That's a big question. So here we can take inspiration from engineering. So if you look at, for example, fluid mechanics and how people design, for example, aircraft wing, you want to study the effect of the wind flow on the aircraft wing, that how much thrust is generated, how much drag is generated, all that stuff. So for that, I don't operate at the level of single molecules in the wind flow. You look at this abstraction called fluid, and then write down Navier-Stokes equation, right? And fluid means not single molecules, but large numbers of molecules, right? Even in a small volume element, right? In the fluid, you will have like 10 power 23 order of 10 power 23 number of molecules, right? And then you describe their collective motion using this abstraction called fluid. And that's a very accurate abstraction. Just because it's abstract doesn't mean it is vague or not numerically precise. It's very accurate. And you study fluid flow using such equations. So if you apply this analogy even to brain, then the conclusion we can draw is don't look at single neurons in the first place, because then you are left with either rate code or spike code. Look at populations of neurons, large numbers of neurons. Look at their average activity or collective activity, and then try to model that. So model brain not as a network of neurons, but network of populations of neurons. So these are also called neural masses. They go by different names: neural ensembles, neural masses, neural populations. But the logic is the same. Look at collective activity of large numbers of neurons, and then write equations for such collective activity. Okay, and so that is in mathematical terms. You have a whole class of models called neural mass models, which look at this average activity. In experimental terms, when you record the activity of a large number of neurons, depending upon the scale at which you measure, it goes by different names. Suppose I am using a scalp electrode and recording electroencephalogram, EEG. That's also average activity of a large number of neurons, but that's a very gross recording with a lot of noise, right? And that's called EEG. But if you put an electrode right on the cortical surface, you get an electrocorticogram, which is also a gross recording, but slightly cleaner than the EEG signal. Now, instead of doing that, if you put an electrode, but slightly blunt electrode, so it's not a microelectrode in the sense that you don't penetrate single neurons. Then shove it in the neighborhood of a bunch of neurons. Then the electrode will record the average activity of a large, maybe order of 1,000, 10,000 neurons. Take that signal, low pass filter it further so that you can get rid of the spikes. You get a smoother signal called the local field potential, or LFP. Now, how about describing all brain dynamics, brain's activity in terms of these LFPs? So think of brain as a network of these small units, these neural populations. And the collective activity of these neural populations, let us describe using LFPs. Then how does the brain model look? This is a question we can ask now. Because if you want to describe brain dynamics in terms of oscillation, which is very common, right? Dynamics is described in terms of oscillation. You divide the entire signal into various frequency bands. And these frequency bands are known for like almost a century. Since the beginning of EEG, right? We've known these frequency bands. People have also studied the significance of these bands under what brain states, what kind of frequency bands are more dominant and things like that. So delta is this 0.2 to 3 hertz, right? You see in deep sleep. Theta is 3 to 8 hertz. So there's a lot of there's a lot of role in learning and memory, especially in the temporal lobe. Alpha again, when you have in a calm state, eyes closed state, you see high alpha from 8 to 12 hertz. Beta is 12 to 30 hertz, and then gamma is beyond 30, and in gamma again you have low gamma, high gamma, and so on and so forth. So each of these frequency bands are given various significances. So if you want a model of brain where you describe dynamics in terms of these frequency bands, you need to use oscillators, right? Now, oscillators therefore seem to be like the ideal middle ground. I want to quote from this science paper by Bazaki and Dragoon. They say that synchronous activity of oscillating networks is now viewed as a critical middle ground linking single neuron activity to behavior. So if you want an ideal neuron model which can express oscillations, at same time in a network structure it can train, it can learn and learn behavior and things like that. Right? That ideal middle ground seemed to be the activity of bunches of neurons, right? The signal and where these different neural populations can synchronize among themselves and so on. That was the insight given. So therefore, oscillator neurons are becoming more popular in the recent years. And actually, oscillating neural networks also are becoming popular in more artificial domain for a totally different reason, nothing to do with biology at all. The roots of that thinking can be traced back to the work of John von Neumann, who is considered the father of modern computing. So way back in 1954, von Neumann seems to have filed for a patent for an idea. He said, if you want to realize Boolean computation, that is binary logic, don't use digital systems in the sense, don't represent 1 and 0 as a high voltage and low voltage, which is what we do in a computer today, but represent binary information in the form of phase differences between oscillators. For example, if you take two oscillators with some phase difference, if the phase difference is 0, then that's the bit 0. If the phase difference is pi, that is a bit 1. Okay, so use oscillators and their phase differences to capture binary information. That was his suggestion. He even filed for a patent on that because he thought that will be a big hit. And the advantage of using oscillators for representing binary information is that oscillators are more energy efficient. If you take an ideal oscillator like an LC circuit, if the L and C are ideal, then it will keep on oscillating forever without using any energy, spending any energy. That's the power of oscillators. So from that point of view, von Neumann suggested that let us use oscillating circuits to design computers. Okay, somehow that line of thinking re-emerged in the last decade. There's a very nice review paper by Xaba and Porot in 2019, where they said it is good to study oscillator circuits, electronic circuits of oscillators, and construct networks of them because they have a lot of applications in low power design. So oscillators are becoming important for two reasons. One is to better capture brain dynamics, other was to design better neuromorphic technology which uses less power. And also with all these computing farms that people are creating everywhere in the world, this data centers and all, the big problem there is an enormous amount of power consumption. So any redesign, any fresh design or innovations in design which gives you low power design will be most welcome. Okay, that's also another point of view for looking at oscillators. So we have seen that a lot of these popular neuron models are all oscillator neuron models. They are limit cycle oscillators. We have seen some in the last couple of days. Maurice-Lacquer, van der Pol, and Hopf oscillator, and so on and so forth. They're all limit cycle oscillators. We have seen all this before. So let us now go back to Hopf oscillator. It's a very convenient oscillator model because in Cartesian coordinates it looks pretty complicated, but if you go to polar coordinates, very simple. The beauty of Hopf oscillator is when you express it in complex variable terms, it reduces to a single equation, which is very elegant, very simple. And we will actually, what we'll do now is we'll use this as the basic unit, the Hopf oscillator as the basic unit, and start constructing networks. Right, and so what we'll do, we will construct first certain generative networks, and then we'll construct deep oscillating neural networks at the end of this talk. First, let us look at a single oscillator, single Hopf oscillator, and let's start studying its properties. Generally, any oscillator is supposed to have a resonance property. That means the oscillator has its own intrinsic frequency. And when you give another oscillating input as external input, then that input also has its own frequency. Then when the two frequencies match, the response of the oscillator should be maximum. And when there's a deviation from that optimal frequency, the response should go down. That's the resonance property. And Hopf oscillator also shows resonance, as you can see in this graph. The x-axis is the frequency difference between the input sinusoid and the oscillator's intrinsic frequency. When the difference is 0, then you have highest amplitude. As you go away from that optimal frequency, the amplitude goes down, and you can see that in this graph. So that is with a single oscillator. Now we want to construct networks, right? So how do you construct networks? So before to that end, let us first couple two oscillators and construct network of two oscillators. So what happens here? So I have two oscillators here, Z1 and Z2, both have the same intrinsic frequency. They are coupled back and forth by two weights. We'll call them W12 and W21. Since both are oscillating, what happens to the phase difference between those two oscillations? So let's take two cases. W12 and W21 are the same, and both are positive numbers. Then what happens is the two oscillators will oscillate in sync. Phase difference is 0, as you can see in this picture. On the other hand, when the weights are both same but negative, the two oscillators go out of sync, go to a phase difference of pi or 180 degrees, and stabilize there. Okay, so which is interesting because you can have two stable values of phase. But the problem is, right, no matter what weight value you take, as long as it is positive, we have only phase difference of 0. As long as it's negative, we have phase difference of 180. But thing is, I want to construct large-scale brane models using such oscillators, which means I should be able to have any frequency and any phase difference. But already I see a huge limitation. I'm seeing only two phases, 0 or pi. Now, how do I overcome this limitation? How can I get any arbitrary phase difference? To answer to that is very simple. Actually, it's there in the equations itself. So here, the weights that we have in the between two oscillators, we somehow assume that they should be real. And then when you assume to be real and they're symmetric, then you have these restrictions. But it doesn't have to be real because the oscillator itself is a complex oscillator. The state is Z1, Z2 are complex states. Therefore, the parameters also can be complex numbers. So W12 can be and W21 can be complex numbers. So that's what we do. And we'll let them be symmetric. And in the complex domain, symmetry means conjugation, right? The symmetric weights here means the weights are complex conjugates, which means if weight, so W12 is equal to W21 star, that gets conjugate. Therefore, you can express the weights like this: some A into e power I5 in one direction, A into e power minus I5 in the other direction. If you do that, you can do some simple math and show that the phase difference between these two oscillators, in this case, will be equal to this phi value. That is, the angle of the complex number which connects the two oscillators, that determines the phase difference between two oscillators. Since you can choose any angle here, phi, you can produce any phase difference between these two oscillators, and it will be a stable phase difference. That means even if you disturb it from that value, it will come back to the same phase difference, which is very beautiful. So you can get arbitrary phase difference. You can see this in a simple numerical example. So here I chose A equal to 0.2 and phi equal to pi by 4. That means I want the phase difference to be equal to pi by 4. Okay, initially I start at some random phase difference. Theta 1 by minus theta 2 is the phase difference. Initially it's some 2 radians or something. Right, after some time it will settle down at pi by 4. Okay, you can see that in the oscillation also at the top. So we're able to achieve arbitrary phase difference. So now let us proceed further. We were able to get arbitrary phase difference, but we are still assuming that the two oscillators have the same frequency. So omega for the two oscillators is the same. Omega 1 is equal to omega 2. That's what I'm assuming here. That's very restrictive because in the brain I have wide range of frequencies, anywhere from 0.1 hertz to few hundred hertz. So how do you get that? So let us start relaxing that condition a little bit. Let us assume omega 1, omega 2 are not the same, but close. Difference is not too much. If you do that, then so let's take omega 1 is equal to 2, omega 2 is equal to 2.2, close, right? Then you couple them with a real coupling, a positive coupling epsilon. If epsilon is 0, then the two oscillators are not coupled, and the two oscillators will go at their own frequency 2.2 and 2. Okay, as you can see in this plot here. In this plot, x-axis is epsilon, y-axis is the independent frequencies of the oscillators. If epsilon is 0, they keep firing at their own frequency. Now keep on increasing epsilon, which means you are forcing the two oscillators to talk to each other. Right? They are at different frequency, but now you are forcing them to talk to each other. So see that When you do that, the two oscillators come to a certain common frequency. After some point, they completely come to a common frequency and they settle down at 2.1. So originally, these two oscillators are at 2.2 and 2. But because I'm using a strong coupling, they're forced to talk to each other. And talking to each other means they have to come to a common frequency. They have to come to some kind of a mid frequency, 2.1. And after that, they keep oscillating at that frequency. Okay, so we are able to make two oscillators with different frequency talk to each other. But in the process, we destroyed the frequency diversity. They have come to a common frequency, which is not good. I don't want that. I want the oscillators to be at their own frequency and still be able to communicate. How will I do that? So for that, I'll tell you what the problems are. So if you try to do that with two oscillators, let's take couple two oscillators with a real coupling, and then let us ask what happens if there's a small deviation. Let's say the two oscillators, omega 1, omega 2, are almost the same. That means omega 1 by omega 2 is close to 1, but not exactly equal to 1. If it's exactly equal to 1, there's no problem. You get some phase difference, which we have seen that earlier. But if it is close to 1, we have seen that if I use a sufficiently strong coupling, epsilon, then I can force them to come to a common frequency. And coming to common frequency is called synchronization. That means oscillating at a ratio of 1:1. So as the deviation from 1 increases, I have to use stronger and stronger epsilon to force them to come to a common frequency. So that is captured by this yellow triangle, right? If frequency ratio is exactly 1, I don't need any coupling at all. They'll oscillate at same frequency and suffix phase. But if there's a deviation from 1, as the deviation grows, I have to use stronger and stronger coupling to force them to come to a common frequency. That's what is shown by the yellow triangle. Similarly, if I have 2:1 ratio, but a ratio of frequency which is close to 2:1, not exact 2:1, again I have to use a sufficiently strong coupling to force them to come to a 2:1 ratio of oscillation. That kind of an oscillation is called entrainment. Again, as deviation is higher and higher, I have to use stronger and stronger coupling to make them come to that simple integral ratio. So with all this, basically the moral of the story is it's very hard to make oscillators have a stable phase relationship and the frequencies are not the same. But this is a simple summary of this. Now what we try first, let us not try to get a constant phase difference. Let us only try to get a normalized phase difference. Right? What does that mean? So instead of looking at theta 1 minus theta 2, let us use the quantity theta 1 by omega 1 minus theta 2 by omega 2. We call this normalized phase difference because you are normalizing each phase by its own intrinsic frequency and looking at the difference. We will ask, can we make this difference constant instead of trying to make theta 1 minus theta 2 constant? And that can be done in a very straightforward fashion by what is called power coupling. To achieve that, basically what we need to do is we need to be able to instantaneously change frequency of a signal from one frequency to another frequency. How do you do that? It's very easy to do that if you use this kind of a complex variable state. That's why we have chosen half oscillator, because for the half oscillator, the state is a complex number. And using this very simple operation, you can change the frequency. What is the operation? Let us say there's an oscillator of frequency omega 1. Its state is Z1, given by A1 into e power I omega 1 t. Now I want to change the frequency of this oscillation instantaneously to omega 2. How do I do that? Just raise the power of this Z1 to omega 2 by omega 1. See then what happens. If you substitute this here, Z1 power omega 2 by omega 1 means A1 into e power I omega 1 t power to the raised to the power omega 2 by omega 1. Omega 1 gets cancelled and you get A1 into e power I omega 2. This oscillation is at different frequency of omega 2. Okay, so now if you take two oscillators, again couple them like before, but only and the two oscillators Z1 is at frequency omega 1. Let us assume it's a low frequency, and Z2 is at frequency omega 2. Assume it's a high frequency. Now these two are connected in back and forth fashion. So when Z1 is sent to Z2 as input, right, at the connection, assume that this kind of a power coupling occurs. That means Z1 is raised to power omega 2 by omega 1. When you do that, what happens is the signal going into second oscillator will be at frequency omega 2. Right. Similarly, in the reverse direction also, you raise the power Z2 to the power omega 1 by omega 2. Then what happens is the signal that goes to omega 1 frequency, the oscillator 1, will be of frequency omega 1. So because of this arrangement, what happens is each oscillator receives from the other oscillator a signal of its own frequency. So there's no problem of entrailment and all that. It's very clean, right? So this kind of a coupling is called power coupling. And when you do this kind of a coupling, using some simple algebra, you can show that the normalized phase difference psi can be made equal to any arbitrary value. You can choose any value, and I can design the coupling so the normalized phase difference is equal to that coupling. So with this one step, I got rid of all those problems, posed by Arnold Tunks and all that. It's a very simple solution, and also biologically plausible. So now, how do you use it to construct networks? First, network means we have to first talk about training. How do you train oscillators? So let us talk about training at level of single oscillators. In case of a single oscillator, what does training mean? So here I have an oscillator of frequency omega naught. I give it a sinusoidal input, right, of frequency omega. Then when you train this oscillator using this training rule, what happens is the frequency of the oscillator moves towards the frequency of the input. Okay, so that means the oscillator is tuning its frequency to that of the input. Right? This is called frequency tracking. So that's a basic kind of training. You can see this in this numerical example. Here I have an oscillator with initial frequency of 40 and external signal as a frequency 30. Then as I keep on presenting the external signal to this oscillator, the oscillator's frequency moves slowly from 40 to 30, matching the external input frequency. So now with this, now I'll construct a network, which is like a generative model. I can use this network to generate any arbitrary time series. How do I do that? I take n oscillators. All the n oscillators are coupled by this kind of a power coupling, what I just showed here, right? And since you have n oscillators, you will have an n by n array of coupling matrix. And the output, to get the output, I add up all these outputs of all these n oscillators using some weightages, alpha I get some output signal, ST. My goal is to make this ST equal to some kind of a desired output, which I will call P teach. Okay, how do I decrease error between P teach and ST? So there's some learning rules for that. I'm not going into the mathematics of this. And if you train this network now, this training typically is done in 2 stages. In the first stage, you have to only train the frequencies of all the oscillators. And in the second stage, you train the weights. So here I'm training this network on simple signal, which is a combination of multiple sinusoids. Right, this combination of sinusoids has different amplitudes, different frequencies, and different phases. So in the first stage of training, so they have some so a bunch of oscillators, I think some 50 oscillators or something. Now the oscillators frequencies are initialized to some random values. And if you look at the histogram of all the frequencies, it looks something like this. Now, after presenting the signal for some time, all the frequencies of the oscillators, you see they are bunched together, close to the frequencies in the input signal. So input frequencies are at 3, 7, and 11. Initially, the oscillator frequencies are all over the place, from 0 frequency hertz to some 13 hertz or something. But after training, all the frequencies of the oscillators are concentrated around the frequencies in the input signal, that is 3, 7, and 11. So that's the frequency training. That's the first stage. After that, you train the forward weights and also this coupling coefficients. And when you do that, you see that the network has learned. You take 2 signals here, it's learned the signals very well. There's only a small deviation in the second signal, but the first output is very accurate. So after this, we got encouraged and we wanted to try this out on more complex signals. So we took some EEG signals, right, and trained the network. We got very good fit. As you can see, it's a 6-channel EEG. And the network is able to learn the time series, the EEG signals very accurately, both in time domain and frequency domain. Okay, and so also this is a generative model, and you can see in this plot that as you increase the number of oscillators in the network, you get more and more accurate fit. Just like in a deep network, as the network size gets bigger and bigger, you can train the network more accurately. You can fit it more accurately to the data. So same thing is seen here also. So with this, now we are in a position to model brain dynamics at a large scale. And one comparison project of this kind is something called TVB, that is the Virtual Brain Project, which is an ongoing project in University of Marseille in France. So these people have this project, they construct large-scale brain models of brain dynamics using networks of oscillators, just like what I'm showing you now. The thing is, there is a big dichotomy that is a challenge that is faced by these models. That is, they can learn brain dynamics very accurately and very well, but they cannot learn input-output behavior, right? Whereas if you look at a deep neural network, which you have done yesterday, they can learn input-output behavior very accurately, but they cannot model brain dynamics. So this is a dichotomy. So the question now is, how do you construct network which does both? That's a major challenge. So I'll show you that with the deep oscillator neural network that I'm going to define, you can achieve both. You can combine both in the same model. So now let us look at the problem of modeling EEG dynamics. In the previous one, I showed an example where you model 6 channels. Now I'll show you an example where we model like some 60 channels simultaneously. And to do this, we'll do a small improvement to the network. In the previous network, I had a network of oscillators, right, and just combine them using a linear sum. Okay, so now in this new improved network, I'll take a network of oscillators, a layer of oscillators, and then you have the output in the top here. Between the two, now I add a hidden layer of sigmoid nonlinearity, specifically tanh activation. And then we train this using some kind of a backprop. The weights are complex numbers, so we use a complex version of backpropagation called complex backprop. We train that and we get fantastic fit. So earlier, so actually the RMS errors, RMSE values here have dropped by an order of magnitude. Earlier I was getting like 0.2, 0.3, things like that. Now it is 0.02, 0.03, things like that. Okay, so we get a very good fit, and that too for a large number of channels. Something like 60 channels. This work was recently published. This is Sayan Ghosh's PhD work. Then we did a similar study with fMRI data also, and this is Anirban's PhD work, right? In fMRI, you have so here again we took the similar kind of a network, but we changed the architecture a little bit to suit fMRI. So in fMRI data, brain is divided into a bunch of what are called ROIs, or regions of interest, typically about a couple of hundred ROIs. And you have a signal corresponding to each ROI. Now you need to train this model so that it can capture the signal at each ROI. So what we do is we have a network architecture like this. We have a network of oscillators, and there is one oscillator corresponding to each ROI like this, and the output is read from one unit corresponding to that ROI. Between this one ROI unit and one oscillator, there is a hidden layer, a specific hidden layer corresponding to that ROI. This consists of sigmoidal neurons, and the oscillators are coupled based on how the ROIs are actually physically connected in the brain. So in the brain, every part of the brain is not connected to every other part. Only some parts are connected. So there is a technology called diffusion tensor imaging, DTI, which will tell you which parts of the brain are connected to which other parts. Or specifically, if you divide the brain into a couple of hundred ROIs, this technology will tell you what is the fiber density which connects a given ROI with another ROI. Okay, so in the model also we use that information to figure out. So that's called structural connectivity matrix. We use that structural connectivity information to define which oscillators are connected to which other oscillators. Okay, like this we set up the network and we train the network. You get very accurate fit, as you can see in these plots. So in the upper plot, we are showing both the actual plot and the desired plot, and both are coinciding almost. You can't see any difference at all. So there's a lot more details right on this. I think you'll be doing all this in your project tomorrow and day after. Then we also define what's called a tonotopic map. Right. So what happens is there are certain areas in biology where the brain constructs a map of frequencies. Right. So one example of that is the cochlea, the inner ear of the right in the ear. So there is a membrane called basilar membrane, which does some kind of a Fourier transform of the input signals. So if the input signal is at, for example, 100 hertz, right, that signal produces an oscillation in this distal part of this basilar membrane, which is all folded into a loop like a snail inside the cochlea. Now, when an input signal has, let's say, 1000 hertz, right, it will oscillate somewhere in the middle. Input signal is 10,000 hertz, it will oscillate close to the kind of beginning of this membrane. So it does some kind of a Fourier transform of the input signal. So different frequencies are mapped onto different parts of this basal membrane. Another example of that kind of a frequency maps is primary auditory cortex. Especially a lot of work is done on primary auditory cortexes of bats. And this picture is from a paper by Nobuo Suga, who has done, a Japanese researcher who has done a lot of work on bat auditory cortex. So here you can see that, so in this class of bats specifically, so bats navigate by echolocation. They send out sounds, and from the return signals, they'll find out how far a given target is, or what's the relative velocity between the target and itself, and so on and so forth. So the signals used by the bat are in the range around 60 kilohertz. Okay, so therefore, in bat's auditory cortex, it allocates certain area to this frequency band. Since a lot of energy is around 60 kilohertz, a lot of area in the cortex is also allocated to that small band of frequencies. But if you go to one end of this strip, right, it will respond 100 kilohertz. At the other end, it responds to 10 kilohertz. So there's almost like a linear map of frequencies in the strip of the cortex. So this is a bat's brain at the top. Within this brain, this part is the primary auditory cortex, this orange part. And that is where the frequencies are mapped. So we have modeled something like this using an array of oscillators, a 2D array of oscillators. And so this array is trained so that, right, the rows, the columns correspond to frequencies and rows correspond to phase differences, right? So if you give a given frequency, right, a single frequency and a signal with a single frequency and a given phase, an entire column corresponding to the frequency gets activated, and within that column, a subset of oscillators will have high response because this subset corresponds to that specific phase. Right, so the entire array maps frequency and phase. Right, a given frequency and phase is mapped onto a given oscillator, given small area inside this two-dimensional map. So that's a tonotopic map of oscillators. Then we also constructed electronic circuits of oscillators, and here is what's called a memristor. Right, a VO2 memristor, which is a nonlinear conductance. It conductance varies as a function of voltage. In fact, we have seen that even the voltage dependent channels in neuron are not very different from this. But this is an artificial memristor. So this kind of memristor placed in a circuit like this will show oscillation. So you can see them here on the right. So we have done phase plane analysis of this, and this is for the VO2 oscillator neuron. It looks a bit like the Morris-Lecar phase plane, which is very interesting. And using such oscillators, we were able to model locomotor rhythms, because in quadrupeds, they exhibit very rich locomotor rhythms, right? Like, they show like walking, trotting, pace, gallop. These are all different names given to different types of locomotor rhythms shown by quadrupeds. So we were able to show all the rhythms by just using 4 oscillators coupled by a set of 4 capacitors. So 4 oscillator circuit, which is shown here, right? You take 4 such circuits, couple them using 4 capacitors. By choosing the capacitor values appropriately, you can make this system show all these rhythms. Okay, then finally we come to a deep oscillator neural network. So in the deep oscillator neural network, you have alternating layers of oscillators and static neurons. The static neurons can be sigmoids or ReLU neurons, or can be anything. But the weights are all complex numbers. And this is the deep oscillator neural network. You can train it using some standard optimizer, which usually comes with the simulator itself. And this network can be trained to solve a lot of basic signal processing problems. Like in this simple example, we are just trying to do autoencoder. That means the input and output are the same. It learns it very well. Then we trained it to perform integration operation, which is a fairly hard problem because you have to integrate all the values onto the past. And it's learned it very well. Then some signal processing tasks like amplitude demodulation. Right, you take an amplitude modulated signal and then feed that into the network. It has to reconstruct the message signal. So it does it, learns very well. Then we progressively gave it harder and harder problems. So this is a video processing problem. You have to recognize action inside a video. So for this, since the input is an image, right, we cannot use this kind of a DOM. We need to use some kind of convolutional version of it. So we constructed a convolutional oscillator convolution neural network, oscillator CNN. We trained it and it works very well with validation accuracy of 99.75 accuracy on a standard data set. Then we applied this to video frame prediction. That means I give a series of image frames, which consist of moving squares, and the network has to predict the next frame in that video. So the top row is the input, the second row is the desired output, the third row is the output of a convolutional LSTM neural network, which is like a gold standard right now. The fourth row is our model, the convolutional oscillator convolutional neural network. You can see that it's much better. This paper is actually recently, just last week or so, it was accepted in scientific reports. So our big goal is to literally create an oscillator theory of the brain. Okay, so in brain, a lot of functions are implemented by oscillations. Like for example, in spatial navigation, sensory processing also, attention, motor function, right? All these things in the back end, right? Brain implements these functions using oscillatory elements. So the thing is, we need to have a good theory of that. So for that, I think this oscillator neural networks will be very powerful. The kind of picture of brain computation that all this points to is something like this. You can compare brain's computations using with radio communication. In radio communication, all communications happens inside the Earth's atmosphere, right? So, so if you, so therefore, you can only operate within a certain frequency range. Because if the frequency is too small, like less than 3 hertz, the wavelength of the light or the radiation becomes so big. It becomes much bigger than the Earth's diameter. So it doesn't come back. You send it out, right? Whereas if the wavelength is too high, then there will be a lot of loss in transmission. It becomes expensive. You need to then pump in a lot of energy so that it reaches the target location. So therefore, if you are looking at radio communication, it can only operate within certain bounds. Okay, so similarly in the brain also, all communication happens between 2 frequency bounds, like 0.1 hertz and like a few hundred hertz. So like if it is less than 0.1, probably it becomes much bigger than the brain size. Well might become much bigger than the brain size. Whereas if it is very high frequency, then maybe there's too much loss in the brain's media. So that seems to determine the bounds on the frequency of operation inside the brain. So brain you should now think of as a continuous medium in which signals propagate. And now computations are done within this medium as signals propagate. So that requires a very different kind of a brain theory. And we hope that this kind of a deep oscillating network will serve as a convenient starting point. But there's a lot more work to be done. We have to apply this network to all these different phenomena, right? And then develop a theory for various phenomena, an oscillator theory for various phenomena. So these are different students who worked on different stages of this project. And thank you. If you have any questions, we can discuss it. Hello. Hello, any questions?
Hello, sir.
Yeah.
Uh, Thanks for the wonderful lecture. I was quite overwhelmed with everything that you said. Like,
Hmm.
it's all new to me, so I'm still processing this stuff.
Yeah.
The one thing I had was like, I know this is still sci-fi, but would it be possible to communicate, like in terms of if it's frequency, would it be possible to communicate thoughts or something like that?
But with other brains.
Yeah.
Yeah. I mean, so actually, I met one guy in Berkeley,
Mhm.
in California. This guy was running a startup. What he was trying to do is he would record EEG from one brain, one head, basically.
Mhm.
And in the second head, he would place a bunch of electrodes to actually inject current into the head. Okay, so he'll copy the state of one head using EEG and use that to stimulate the second brain. His idea was to copy the state of one brain head into the second head. So that's like communicating thought directly. I don't know what is
Yeah.
the success of that because I haven't followed up that line of work. But such things are being tried. But so reading thought is now is a done deal. It's there's a lot of we also have done some work on those lines. Suppose you are visualizing some image, right?
Mhm.
You pick up the EEG signal, and if the image come from a small set of images, then it becomes a classification problem. So that is quite doable. We have done that kind of work. But the question then is, how do you inject that information back into another's brain? That I have to see what is the latest in that. But it's not impossible, I think. It's quite doable.
Yeah, like I was curious because of this. I was curious because like recently I learned that when you give the cochlear implants, what they basically do is they give input to the cochlea,
Hmm.
even though if the person was deaf beforehand, over a period of time, the brain or the cochlea learns the input signals and they are able to hear. So that's why I was curious. That would be possible for the thoughts
Yeah,
as
so
well.
that's only sensory, right?
Yeah.
Yeah, correct. Yeah, it is, I think, in principle possible. I haven't been following up. Like, what is the latest on?
Hi, Srinivas sir. Varsha
Yeah,
here.
for sure.
Yeah,
Yeah.
I was just following up on what he was saying. So
Hmm.
theoretically, because we are assuming that brain computations can be like oscillators. So and the
Yeah.
oscillators actually learn. So
Hmm.
then, theoretically, can we prove that we can actually make the brain learn that particular frequency, say somebody else's frequency? Can that be
No,
theoretically
but
shown
no,
in the oscillator model?
a given person doesn't have a single frequency, right? A brain has a wide range of frequencies.
Mm.
In the oscillator, single oscillator, I've shown you how it can learn the frequency of the input signal.
Yeah.
It will track the frequency that is there.
Mm.
But the whole brain level, there's nothing like learning another person's frequencies because everybody has a wide range of frequency, 0.1 hertz to a few hundred hertz,
Mm. Mm.
right? So the
So
only
at network level, it's like
it
that
has no
learning
meaning.
idea cannot be expanded, is it?
No, you can. The only thing is there is nothing like single frequency there.
Okay.
Because in the example that I've shown, let me share. Right, you train the network, but what it is learning is the entire signal. It's not just learning one frequency. So here, for example, I teach it to take input signal is some I of t. Output is this O of t.
Yeah.
Okay, and it will learn, it does whatever it needs to do inside, and then it will learn that mapping. Just like your deep network.
Yeah.
Only thing is the training happens in the hidden layers with all these oscillators.
Yeah, I was thinking more in terms of, say, for example, neuromodulation, where you are applying TMS at a particular frequency and trying to entrain that frequency on. Can we
Yeah.
actually model that?
Yeah, I think so. Because so then if you model the, so let's say you are trying to do TMS to improve some visual function, the motor function, something like that.
Yes.
Then you train a network to do that motor task,
Yes.
the oscillator network. Then you apply your oscillatory input to some oscillator hidden layer in the network and see if you can reproduce the results.
Okay.
In principle, you can do that kind of thing. So
Okay.
in fact, the oscillator network opens up another possibility for TMS. Because in TMS, although you give pulses, you don't think of them in oscillatory terms. Because if it's really oscillatory, then you should think in terms of resonances. Right? Brain has resonances. So you need to make use of the resonances to give, like, mild pulses but get a lot of effects, but get strong effects.
Yeah.
TMS actually doesn't work like that, whereas all that is possible. And oscillator networks can serve as a platform for developing such simulation protocols. Yeah, all that is research in the future. We have to do all
Yeah,
that.
that would be cool. Yeah.
Yeah.
Thank you so much. It was
Varsha, may I ask your background? Do you work in TMS and all?
sir, I am your student. Like,
Oh, you are that Varsha. Okay.
yes.
So yeah, very good. Correct. It's in principle all that is possible.
Yeah.
But actually, if you want to work with us on that, we can initiate some activity.
Yeah, that would be nice. I'll catch up with you.
Oh, great. Where are you
Yes.
right now?
I was with Nivedita, so I'm just back home. I'm just
Okay.
starting my own
Yeah.
transit.
Let us exchange mails and do something.
Sure.
Yeah.
Hello, sir.
Yeah, Harsha.
Good afternoon, sir. Sir,
Yeah.
usually lot of papers we are seeing in LSTM based networks.
Yeah.
So comparing with that, this oscillator networks is having any more advantage based on
Yeah.
training and all.
So oscillator network use very small number of patterns. We have done all those comparisons in our papers, especially oscillator networks. Hello.
Hello, sir. I'm
Yeah,
hearing.
it will use a very much smaller number of parameters.
So for
Therefore,
understanding more depth about this one, can you suggest some papers or?
So our recent papers, you can see if you go to our website.
Okay.
Look at Sayan Ghosh's papers. He has a couple of papers.
Okay, sir.
He has done this comparison in great detail.
Okay, sir. Thank you.
And we also have another neuron model which we developed almost 10 years ago. It's called a flip-flop neuron. This is inspired by the flip-flops in
Sir,
electron. Hello.
Sir, that was day workshop sir suggested that paper and we had downloaded that one and we read that paper.
Yeah. So what we are doing now
Flip-flop
is we are
neurons.
using both flip-flops and oscillators we are using. They give good results.
Oh,
Right. Flip-flops or
okay,
memory
sir. Thank
oscillators.
you.
Yeah. It's there in Sayan
So
Ghosh's paper.
comparing with these three flip-flop neurons is giving much better results.
Sorry?
Comparing with all the three models, flip-flop neurons is giving better results, sir.
Flip-flops, both flip-flops and oscillators give you more compact networks, fewer parameters.
Okay.
Oscillators are important because you can interpret the signals in terms of frequencies and all that stuff.
Okay, sir. Okay, sir. Thank you.
Thank you. Anybody else? Any other questions? Anybody coming from more experimental side, neuroscience, neurobiology?
Hi, sir. Rohan here. I was
Yeah,
just,
Rohan, yes,
we
yeah,
will be having a workshop session in the afternoon, so
yeah,
we'll be talking about how these networks are trained and what are some advantages of such networks.
yeah. Okay, no, I'm just curious if like any external people have any questions on this and what they can learn out of this and all that. But anyway, you have afternoon session, where you can also address all these questions. So if there are no more questions, we can wrap up and thank you.
Sir,
Yeah,
this is Varnika. Hi,
yes,
sir.
Varnika, hi.
Thank you for the session. So I'm
Yeah.
coming from this TMS background only. My
Mm.
background, I work related to motor functioning and how brain muscle coordination and everything, motor learning memories.
Mm.
I wanted to know like how, so you were talking about the TMS section, right?
Yeah.
How you can train the neurons and make them do a certain task. I'm more curious, like how can I reach at that point of uh, analysis? Like I have
So,
behavioral data. Like in our lab, we have behavioral data. So,
okay.
is there a way I could utilize that behavioral data to
Now explain your
understand?
behavioral data. What is your task like? What is the animal? Is
So
it?
the task is basically a reaching point task.
Mm.
We usually perform motor adaptation related task.
Are you from Pratik Mutha's lab?
No, no, no. Neeraj
Okay.
sirs, Neeraj Kumar.
Okay. Cool. Yeah. Mm.
Yeah, so can you help me reach at that point of time where I could utilize the behavioral data and understand the oscillation part here?
So you can train this network to reproduce behavior very easily. Reaching is very simple. But if
Okay.
you also have some kind of electrophysiology data, right?
Uh-huh.
This is on humans or what is animals?
Human.
Yeah, okay, but then you'll only have what? Do you have any electrophysiology data, EEG or something?
EEG data I have related to skill, not adaptation.
Yeah, probably see because we were able to train these networks, DAWNs, on both behavior and brain dynamics simultaneously. Cyan has done it,
Okay.
right? So if we have that kind of data, we can try to model that, using this network, both skill learning and the EEG activity.
Okay, so is there any published paper where they have done the task so that I could
So
understand?
we have a conference paper already published. The journal paper is under review. We have cleared one review, but I think I'll ask Sayan to share the. Hey Rohan, can you ask Sayan to share the conference paper?
Yes, sir. Yeah.
Right, that will get you started, and then once the journal paper is through, we can share the full paper also.
Okay, so I'll text Rohan regarding the paper so that I
Right,
could
right.
understand.
So
Thank you so much, sir.
you working with Neeraj Jain?
Neeraj Kumar, Dr. Neeraj Kumar,
I don't know.
IIT Hyderabad.
Okay.
Sir, I have a question.
Shubham, yes.
Thank you, sir. Sir, yeah, actually, this more than TMS, this TSCS or alternating current stimulation is more likely to entail that
Correct. Yeah, more
oscillatory
suitable.
circuit.
Yeah.
I work on EEG and quantitative EEG and TSCS. And what is the right approach we can begin with to
I mean, if you
give a
have data
proper?
of that kind, so thing is, we can use the Dawn as a platform to develop protocols, and TSCS is more ideal because it's oscillatory, right? And we
Yes.
can, because if you want to look for resonances within the brain's response, that's much harder to do in a live brain, whereas in a simulation you can do that. But that's a whole line of research, because we have just published the first paper on Dawn. Okay, just last week it was accepted, right? So there's a lot of research that has to be done, but in principle it can be done.
Okay, sir. And it's wise to do it offline signal processing and finding the frequency and giving the stimulation with TSS, or it's online is more accurate. So,
No, so what I'm saying is, if you want to find the resonances, it might be harder. There may be more practical constraints to search the entire frequency space and then find out what is suitable, right? Because your ethics committee may not even allow those protocols. It was never tried. So you have to do animal work and so on. Whereas in a simulation, you can do whatever you want. If you find a good hit, good some very unconventional frequency where you're getting good response, at least that will give you like a hypothesis. So you can at least apply for that and do research in that direction. But
Okay,
this
sir. I'll
basis
try
simulation
this.
is more ideal for this kind of models.
Okay, sir. Thank you.
Okay, thank you. Anybody else?
Hi, sir. This is
Prashant
okay.
Shah. Yeah.
Yes, sir. Sir, I was just curious that since the model requires a lot of data, I was just curious if we could use EEG data if, let's say, I want to model attentional states, internal versus external. And if I have EEG data, but the tasks were different, would it be helpful or would it make sense to use all the EEG data that were studying internal versus external state, irrespective of the task, and use those data sets to train the model?
Yeah, so let me see if I understand your question correctly. So depending upon the task, there may not be need to model all the channels. Right? You just take the channels which are relevant and only model those channels. So for those, so that means you train the network on the behavioral task, right? And also model it to produce only those relevant EEG channels. That can be done. Is that what you're asking? Yeah.
Okay.
Hello.
Riddhi, yeah.
So this is a follow-up on Varnika's question. We also, I'm from the same lab, by the way. So we also are working on collecting TEP data. So do you, Varnika?
Cranial evoked potential. So we basically simultaneously record EEG and understand the potential when TMS pulse is transferred.
Okay. Oh, yeah.
So
yeah.
would it be, so will the model be better suited for
Yeah, in
TEP?
principle, this can be done because I have one of my former students. His name is Vignesh Muralidharan. He works on TMS. He is at IIT Jodhpur. Okay, and we have gone through all these discussions with him. Right, we really want to initiate some research, but just that we don't have a project to initiate all this. But all this has to be tried out. I mean, I cannot give a definitive answers unless we do some work on this. But TMS would be a great application area for this class of models. I mean, if you can put me in touch with your guide later, we can discuss and see what can be done. It's a good problem for this. Yeah.
We will do that.
Yeah. Great.
Thank you.
Thank you.
Thank you.
Okay, so let us wrap up. I hope you found something useful in this session, and afternoon you'll do the practical sessions correspond to this using these networks. So, thank you.